Hi, listeners. Welcome to episode 11 of the ALD Stories podcast. For this episode, I go to Seattle, where I sit down with Professor David Bergsman, an assistant professor of chemical engineering at the University of Washington. David is a new professor at UW, starting his tenure in 2020 after receiving his PhD from Stanford under the direction of Stacey Bent and a postdoc at MIT with Jeffrey Grossman. His work primarily involves membranes, thin networks of polymeric or ceramic materials used for industrial filtrations and separations, like water desalination or gas purification. David uses a process called vapor phase infiltration, or VPI, to fabricate and modify membrane surfaces in an attempt to decouple the synthesis property relationship. VPI, also known as SIS or sequential infiltration synthesis, is derived from an ALD process with cyclical exposures of precursors, but the substrate is often soft, allowing deliberately longer chemical exposures to facilitate diffusion into the material and creates a hybrid material rather than creating hard interfaces and conformal films. In fact, early iterations of VPI were done in exactly the same way as ALD, with the only difference being longer exposure times. VPI has been used to dope conductive polymers, enhance the mechanical properties of polymeric fibers and composites, and enhance oil absorption in foams. In this episode, David and I chat about how his MLD work in Stacey Bent's group inspired his now lab, challenges associated with membrane properties, and how vapor phase infiltration can help, and what it was like for him to start an ALD lab in the middle of a pandemic. As always, big thanks goes to my guest, David, for letting me take up some of his morning and for being so candid. So grab your tea or coffee, and please enjoy episode 11 of the ALD Stories podcast.
Welcome to ALD Stories, a series of conversations where we share the untold stories of atomic layer deposition and the people behind the technology. This podcast is brought to you by Venec, the home of ALD.
David, thank you so much for joining me today and taking some time out of your morning to talk with me. Like I mentioned before, you now have the distinct honor of being the furthest geographically from me out of Washington State. I am over here in Finland after just recording with somebody live in Helsinki. So this is very nice, but I haven't talked to somebody from the US here in a couple episodes now, so it's great to have you here.
Thank you.
Coming to us from the University of Washington, after, as you mentioned, a PhD with Stacey Bent at Stanford and then postdoc at MIT, and a relatively new professor at University of Washington, right?
That's right. I've been here about a year and a few months now.
Hey, perfect. Yeah, I think it'd be cool then we can kind of go through your whole ALD MLD history, because it hasn't been so long. We don't have to go back decades. We have to do for some people. But maybe before we get into the stuff you're doing at Washington now, we rewind back to your time at Stanford. You tell me a little bit about the work you did with Stacey Bent and how that kind of has progressed to where you are now at University of Washington.
Yeah, absolutely. So when I went to Stanford, I originally went and was intrigued by Stacey's work because of this really strong focus on sort of fundamental surface engineering and molecular behavior. I thought that was fascinating. I love nanotechnology. And at the time, Stacey had kind of projects in a lot of different things. What most intrigued me was her work on molecular layer deposition, sort of the organic analog to atomic layer deposition. For its ability to, rather than growing these metal oxides, to grow polymers, or at the time we were starting to see a lot more work in these kind of hybrid organic, inorganic materials. And so my PhD focused on trying to better understand sort of the molecular structure of organic grown films. Because kind of really early on in the film, there was a kind of a general belief that when you're doing this layer by layer growth process with organics, you can kind of imagine maybe each layer is going to sort of self-assemble. And it's much like self-assemble monolayers, files. Sure. So we kind of had this vision that every time we exposed a surface to an organic molecule, it would sort of stack up into effectively a single layer. And so when you expose the second monomer, you'd grow sort of a second layer. And as you repeat this process, we sort of envisioned kind of a, layer one of monomer one, layer two of monomer two. And what we actually discovered over time was that this is not the way these organic MLD films grow at all. It's actually a very complicated soup. The molecules are strongly attracted to one another with intermolecular forces. They grow in sort of a variety of different angles. And we sort of generally found that the the backbone structure of these molecules has a strong impact on the resulting structure of the films. So if you, much like with regular kind of polymers grown in solution, if you have consistent backbone chemistries, you'll tend to grow more crystalline structures. If you grow polymers with a variety of backbone chemistries, you'll grow kind of more mixed structures, more amorphous structures. And we discovered that a lot of MLD growth is not this kind of layer by layer process as you might expect. There's this constant behavior where molecules will react twice with the surface and self-terminate and sort of reinitiate, because you could have molecules kind of fusing in and sort of seeding new growth. And it turns out the competition between termination and reinitiation is what leads to this steady state growth behavior. And so a lot of my work was sort of in just understanding how these MLD films grow. We did a little bit of work with these pure organics. We also did some work with hybrid organic inorganics, making manganese-based hybrids for catalysis, and a little bit of work on just subcell monolayers as well. And from there, I kind of had this experience with these technologies and a little bit of catalysis. And I started to gain a little bit of interest in how we could sort of apply these technologies to other areas. And one area that seemed really promising was in membranes. Membranes are a technology where we use a very thin separating layer with precise molecular structure and behavior to separate various chemicals of interest. And that seemed like a perfect application for technologies like ALD, like MLD. So that's why I transitioned to my postdoc with Jeffrey Grossman to study kind of membranes and how we can use some of these tools in that space as well.
That's fantastic. So yeah, it's interesting. People don't usually pick MLD over ALD when they're studying things. MLD tends to be the more challenging to understand. So kudos for you. I did a tiny bit of MLD during my PhD as well. So I'm familiar with the struggles, and I think a lot of the things I've read your paper on the mechanism as well, are all very much important in understanding what was happening in my films too.
I think what makes it so hard is that ALD is almost a self-cleaning process. The monomers, like trimethylaluminum, not only does it sort of neutralize itself when exposed to basically anything, water, whereas with these organics and MLD, they're sticky. They have strong hydrogen bonding. And so the consequence is that you dose one of these organic molecules and it's sort of in the chamber almost forever until you run one of these cleaning processes again.
So it's cool that you are working with membranes. I think it's not a very, very common field or common application, at least so far that I've seen in the atomic layer, molecular layer processing community thus far. So it's really nice to see that somebody is kind of taking the initiative and driving these projects. Now, where do membranes then fit into kind of the overall context of the world? I suppose their impact, and then we can talk about then where does the MLD and the ALD and the atomic layer processing come into play?
Absolutely. So membranes and separations in general are becoming an increasingly important area of really the energy community of the world. So I think Ryan Lively at Georgia Tech published a relatively famous paper called 7 Chemical Separations to Change the World. And in it, he somewhat famously said or reported in his group members that something like between 5 and 10% of all energy in the United States is consumed in separating chemicals. And that's a huge fraction of our energy consumption. Industrial processes is something like 30% of the energy consumption in the United States. This was at the time. And part of the reason for this huge energy consumption is that one of the easiest ways to separate chemicals is in high volumes is to use thermal distillation. We essentially pipe in a mixture of 2 or more reactants, and then we boil them in a distillation column, fractionating them into their various components based on their boiling points. It's very effective, and it can be used even for molecules of very similar character, but it's also highly energy intensive because you're effectively limited on some level by Carnot efficiency. You're using a temperature to drive the reaction, and you can't recover more than some fraction of that back into electrical energy. So the strategy that could be very impactful is to transition away from thermal distillation towards other separations that are more energy efficient. And membranes are potentially a fantastic option for this, because you can recover something like 97% of the energy you use for driving this pressure-driven separation. The idea, of course, of a membrane is you basically have a filter. It either has some explicit holes or pores, or the membrane itself is able to solubilize one reactant over the other. And the net result is if you apply some pressure, there's a driving force for the molecules to diffuse through that separating layer. Either because, say, one of the molecules is larger than the other, and therefore the small one passes through the holes, the larger one stays out. We call that size exclusion. Or the membrane is able to solubilize one of the two reactants selectively. And as a result, the one that can diffuse into the membrane is passing through, the one that cannot is sort of rejected and left behind. So it's far more energy efficient to do the separation. The big challenge is that we have been using these membranes successfully in some fields, but not others. So membranes have been used in say, desalination for the past 70 years very effectively. It's far more efficient to use reverse osmosis to remove salt from water than to boil the water to try and get out the pure water from the salt. But in other areas, say in organic separations, the membranes are not stable in the things we're trying to separate. You try and separate organics, the organics will dissolve these polymer membranes we've been using. And so we need kind of new methods of creating these membranes that are also cheap and affordable, potentially easy to implement in order to transition to the use of membranes and save all this energy from doing these industrial separations.
Sure. There needs to be some way to do it that also isn't super energy intensive, I imagine. You know,
exactly.
Use the energy efficient process and then cannibalize it by the modification of it being very energy intensive. Sure.
Exactly.
Yeah. So membranes are used for water desalination, for these organic separations. It's so then that these industrial separations are more of the organic separation side that they're doing the distillation for.
That's certainly where we'd like to be using some things like membranes or some other separation strategy. Gas separations is also a large consumer. Petrochemicals and chemicals, so separating oils, separating things like benzene from toluene, from the different xylenes, propane, propylene. These are all common separations in both oil and chemical processing that we need to perform, but we currently can't do with membrane separations because the membranes, or at least the polymeric membranes that are cheaper, dissolve in the various solvents.
So then these challenges that we have with the membranes, what is the ultimate solution then? A perfect membrane that would do these separations. What do they need in order to be effective that they don't have right now?
Yeah, so there's a lot of things that need to be addressed in the membrane space. But I think the three biggest issues that we're facing are one of selectivity, one of stability, and one of cleanability. So for instance, one of the biggest challenges is if you want to separate various chemicals that are essentially the same size or essentially the same character, you need a membrane that is able to distinguish between them. So take various xylenes as an example. Xylenes being like a benzene ring with two methyl groups onto one of the various positions, ortho, meta, para. They're very similar in chemical structure and chemical properties, with very subtle differences in things like their boiling points. If we want to separate those sorts of things, we would need a membrane that can interact with those materials in a different way. And right now, the membranes that we can come up with are not very good at distinguishing between those. We need changes in either the solubility of those monomers or the diffusivity of those monomers through the membrane. You have a similar problem with gases. Gases are a very similar size, and they tend to not interact much with a membrane. So if you want to improve selectivity, you need a membrane that essentially dissolves either one of the gases more or less readily than the other, or allows one of them to diffuse through the membrane more easily. There's also a problem of stability. So existing membranes are typically polymeric, those are cheaper. We can also make membranes that are ceramic, that are far more chemically stable. They don't dissolve in the organics that we might be trying to separate, but they have other challenges. They're far more expensive to manufacture, something like 10 times more expensive. Mm-hmm. And they tend to be a little bit more brittle. But they do have the advantage of being relatively easy to clean. They can achieve selectivities that are comparable to what you can achieve with polymeric membranes. It's just they're very expensive to produce, typically because you essentially have to make these small nanoparticles and then sinter them together at a high temperature. The last challenge is that most of these membranes are difficult to clean. So if you make a polymeric membrane and say want to use it for water treatment, you'll slowly accumulate biophallants on the surface of that. And removing those biophallants is often quite challenging. One common method of doing that is to treat with things like bleach or some other chlorinated oxidative agent. And the problem is that many of these polymeric membranes tend to dissolve or degrade in the presence of these the presence of these cleaning agents. So we need a membrane that is more chemically stable and has better ability to select between various materials, and one that's easy to clean. Ceramic membranes, in some sense, are able to achieve most of these, but at considerable added cost. Polymeric membranes suffer from kind of essentially all of these, some difficulty in selectivity, and a much lower chemical stability and cleanability. So trying to find ways of basically making something more like a ceramic membrane that's cheap is really in some sense, the ultimate goal.
Maybe some people hearing that will understand where this is maybe going then. So then, so now to your lab and to your work, what is your approach for trying to solve these challenges? Are you going the route of trying to make lower cost ceramic membranes, or are you trying to change these polymeric ones, modify them to be more ceramic-like, and to address them in that kind of low cost fashion then?
Yeah, so a little bit of both. So exactly as you point out, if the goal is to basically make something more ceramic-like, the trick is to find a way to do that in a way that is cheap. But there's kind of a hidden goal, which is that even if we could come up with something that's relatively inexpensive, it would be difficult to convince some manufacturing company that this is a technology they should consider. So there are lots of different ways of making chemically stable membranes, graphene oxide or other ceramics that are cheaper. You take this information to one of the membrane manufacturing companies and say, hey, we have this great technology for you. Go forth and use this to improve the world. And they will say, that's a huge capital investment for us. It's unlikely we would consider that until the technology is far more improved. You need a much further along technology level. So that can force you to go back to the drawing board and try and make a startup company and try and develop these technologies. So that's a challenge. So what we're trying to do in my lab is we're trying to kind of circumvent this process by creating additive technologies. So not trying to kind of reinvent the wheel for how we make ceramic membranes, try and make this cheaper. Instead, we're trying to take existing manufacturing of membranes and provide some added incentive to make these membranes better. So some added value. So to do that, we're doing things like taking polymeric membranes and infiltrating them with inorganic reactants, metal organic precursors, or sometimes even organic reactants to try and improve their chemical stability, to try and make them more stable while still maintaining their flexibility, perhaps even more selective. And we're trying to find ways to, say, create new selective layers using some of these vapor deposition tools so that the membranes, or at least the support layers, can be more effective at separating these chemicals. And again, all with the idea of taking some existing membrane and improving it, because then we can go to these companies and say, you have this existing manufacturing, that's great. here's an added tool you can put in right at the very end of your manufacturing line that will give you added value to your membranes. And suddenly it sounds like a lot more of an interesting idea to many of these membrane manufacturing companies.
Yeah, that's great. I'm going to get ahead of myself because I'm thinking about the implementation of this in the industry now, and I'm thinking in my head about like roll-to-roll methods and things like that. But I will not get too far ahead of myself, and we'll start just okay. So you're talking about infiltrating molecules into these polymeric membranes, I presume, at the surface, and this is a technique that has a particular name, or has many names, I think, which is.
So depending, you're splitting hairs a little bit, or we will be splitting hairs a little bit, but it uses names like vapor phase infiltration or sequential infiltration synthesis. There are subtle differences between when people have referred to each, but Mark Lasego and Ryan Lively have often used terms like vapor phase infiltration to refer to the process very generally of using these metal organic precursors, exposing them as a vapor to these polymers and allowing those monomers to diffuse, not just between pores, but actually in between polymer chains themselves, to modify the chemical and mechanical properties of the underlying polymeric material. If you repeat this process several times, people like Jeff Long and Seth Darling at Argonne, Alex Martinson, refer to it as sequential infiltration synthesis, where rather than just using, say, a single cycle, you're repeating this process, infiltrating first with metal organic, then infiltrating a counterreactant like water, then infiltrating another metal organic, and so on. Yeah, so a lot of different names for the same process. So a big part of what we do in my lab is in trying to use these infiltration to kind of broadly include both, using these infiltration processes to either infiltrate metal organics to try and improve the chemical stability, or infiltrate even organics to try and create networks within the polymers that still improve the chemical stability of the polymer without, say, making the membranes more brittle.
Sure. I think this is a really interesting process, and part of why we're talking about it here, you and I, is because, as you just mentioned, say a metal organic precursor and then a co-reactant, and cycle that, it's very similar to an ALD process for sure. And I think it's very what the word, maybe elegant, because this process of this diffusing into membranes or into polymers, for instance, was an issue, or originally was an issue. Nobody wanted the ALD precursors to go into the polymers. We wanted a nice, clean interface. Why are they going in there? And everybody tried to stop it, myself included. Yes. I was trying to do some MLD, ALD nanoeminics, and it was a nightmare trying to microdose or something like that to try and prevent this from happening. So I think it's very cool that this is now been figured out a way to utilize it and make it a good thing and not a bad thing anymore.
Yes. When I tell my students about it, it's they often ask me, what's the difference between ALD and infiltration? They seem the same. And essentially what I tell them is, at some level they are the same. It's just in one case, your substrate is either non-porous or your objective is to coat something rather than diffuse it. Whereas in the other case, you use longer exposures, your goal is to diffuse in the polymer. And yeah, they're otherwise very similar. And that's why they're so compatible.
Then for people who may not be familiar with sequential infiltration synthesis or the VPI and so on, it is a cyclical process where you are dosing and purging, right? And basically doing an ALD type process.
Yes. So in fact, the reactors we use for doing infiltration synthesis are essentially the same as a traditional ALD reactor. The main difference is we change the recipe so that the reactant is, well, so often it's a little more resource efficient to block off the pump so that the reactant can sort of stay in the chamber for longer. And we essentially just let it soak into the polymer for, rather than only a couple of seconds like you might do in a traditional ALD process, we let soak in for 5 minutes or sometimes an hour, much longer times to allow these metal organics to diffuse into the bulk polymer. But otherwise, exactly as you point out, it's a cyclical process. You first dose the metal organic, you soak for a while, you dose in a counterreactant like water, you wait for a while. And in some cases, you repeat that process in order to build up or introduce more metal oxide, in that case, into your polymeric material.
So what is actually happening in the polymer then? If somebody may be listening to this and thinking, okay, are they making aluminum oxide, for instance, inside of the polymer, or is it incorporating itself into the matrix? So what is actually going on in there, and then how does that affect the membrane?
Yeah, it depends strongly on the reactants being used. So one of the more well-studied metal organics and polymers would be something like trimethyl aluminum into polyether sulfone. So polyether sulfone has ether groups and sulfone groups with this kind of double bonded oxygen. The general belief is that trimethyl aluminum diffuses probably in sort of a hopping mechanism between the polymer chains. It is attracted to the sulfone, the oxygen in the sulfone groups, but doesn't necessarily chemically react with the polymer. But the association is strong enough that when you sort of dose this trimethyl aluminum, it can sort of diffuse into the polymer, potentially even hop between these kind of sulfone groups, or simply diffuse through the bulk polymer. When you get to the purging step, this partial association kind of keeps the trimethyl aluminum I don't want to say trapped, because if you purge long enough, you could imagine you would sort of remove the trimethyl aluminum, but it provides some thermodynamic incentive to stay associated with the polymer. And so that when you purge, you essentially only remove the excess trimethyl aluminum in the chamber and not remove any trimethyl aluminum, or not a lot of trimethyl aluminum, from within the polymer. But that can change depending on the polymer that you're using. So if you have, say, free alcohols within your polymer, you could imagine the trimethyl aluminum will react with that alcohol to form these alkoxide type structures that are famously water sensitive. And so the mechanism is very strongly dependent on the reactant being used in the polymer. In some cases, if there's very little association, you're forming either nanoparticles or nanoribbons, sort of these aluminum oxide structures. In other cases, you're actually directly reacting with the polymer, and it's almost like a cross-linking behavior. You have these sort of polymer strands. If, again, using trimethyl aluminum as an example, the trimethyl aluminum can react with, say, several different groups, or associate with several different groups, kind of holding everything together a little more tightly. And the result is that the mechanical properties of the polymer are changed. They tend to be a little bit more brittle, but they're also a little bit more chemically stable. They're less likely to dissolve, because it's much like a cross-linked polymer. A cross-linked polymer with this trimethyl aluminum cross-linker is less likely to be solubilized by various kinds of solvents. So the chemical structure is modified slightly depending on the chemistry, but at the very least, the mechanical properties are affected. And trying to play around with kind of the various reactants and how they interact with the polymer is, I think, a big part of what's still unknown in this space, and where there's a lot of room for potentially making these kind of improved membrane designs.
So this infiltration, and with we'll use TMA and water for just the example, because why not? For
well known.
Everybody will be familiar enough with that system at least. So these challenges that you mentioned earlier, the selectivity, the stability, the cleanability, which of these does this end up addressing? Does it address all of them? I know you're getting closer to a ceramic type membrane at that point, or is it only addressing some of them?
Yeah, so it depends on sort of how the process is used and in what circumstance. So for instance, there's some work that has been shown where if you use this infiltration process on something like a PIM, so a polymer of intrinsic microporosity, these are becoming increasingly interesting in gas separations, where it's very difficult to make a membrane that separates two gases. So we create these so-called polymers of intrinsic microporosity. They have very rigid polymer backbones, and so they kind of create this intrinsic porous structure. The challenge is that it's very difficult then to modify that porosity. One thing that has been done is we have this existing pore structure. If we infiltrate with trimethyl aluminum or some other reactant, we can slightly shift the pore sizes within that polymer. And the result is that we can modify the selectivity of that membrane for various gas separations. So in that case, the objective is to sort of have these aluminum oxide groups serving as sort of like partial blockages within the kind of porous nature of the pin. And so in that case, you're actually improving selectivity. There's also been pretty extensive work done by, say, Mark Lisego's group, where they've shown that doing this infiltration process with trimethyl aluminum, I think Ryan Lively was also on this work. If you infiltrate something like PMMA, polymethyl methacrylate, with trimethyl aluminum, the cross-linking behavior of this trimethyl aluminum essentially makes the polymer more chemically stable. And so the result is that you can expose these membranes or polymers to solvents that would normally dissolve the membrane, toluene as an example, and the polymer dissolves much more slowly. So kind of the application of where you use this infiltration process and sort of how much you use has a strong impact. One previous work that I did in my postdoc was we used this trimethyl aluminum to improve the thermal stability of these polymeric materials. So what we found is that if you take a polyether sulfone membrane and infiltrate with trimethyl aluminum, the membrane still will, say, soften or melt above a certain temperature, but the structure of the membrane doesn't change very quickly as a result of the inclusion of these aluminum oxide groups. And the consequence is that we could, say, hit it with a CO2 laser and burn the polymer membrane into a conductive graphitic film without changing the underlying structure of the polymer membrane. So there's a lot of different ways we can use these tools to modify either the chemical stability or thermal stability, or even perhaps the selectivity of these structures using these type of infiltration techniques. But one thing I did want to say too is that I think the reason why this approach to making these materials is so powerful is because atomic layer deposition has such a history in industry already. So there are many different ways of trying to make some of these ceramic materials, but ALD and MLD type tools, vapor phase infiltration, atomic layer processing in general, relies on equipment that's been used in semiconductor for the past 20, 30 years. So transitioning those technologies to new areas is relatively cheap. And we've already seen that transition in spaces like solar cells and in batteries, where creating passivation layers with, say, alumina has become mainstream. The solar cells we get out of China or in companies, I think like Toyota, the electrodes in their batteries now have these thin passivation layers grown using atomic layer deposition. So these tools are a relatively easy transition towards other spaces like membrane processing. It also has the advantage that we don't have to worry about things like the solvent. So typical modification strategies require you dissolve some reactant into a solvent and then get that solvent to expose to the surface. That can be a huge challenge, either because the polymer itself, the polymer membrane, say, aren't chemically stable in the polymer or in the solvent of interest, or you have to worry about wetting the entire membrane, which is a challenge. Many of these solvents won't necessarily wet the underlying polymer material. Or you have to worry about solubility of the reactant in your solvent. We can avoid all of these issues using these vapor phase strategies, because the vapors, there's no solvent, they can diffuse deeply into these polymeric structures, diffuse in without using a solvent. We don't have to worry about destroying it.
This is a good segue then, because I wanted to ask, this seems like it's very ripe for scaling up for industry. It seems like there is definitely an opportunity to do so. And I imagine you've probably thought about that a little bit.
Yes. So atomic layer deposition is starting to see a transition into these roll-to-roll processing tools. I know Steve George in Colorado has developed many of these sorts of tools, and there's a lot of work going on in Europe as well, with basically the transition from this temporal reactor. You stick something in and sequentially dose these various reactants into roll-to-roll processing, where the vapors are exposed to the surface and separated by typically a vacuum or nitrogen screen. Traditional membrane processing occurs at a rate between 10 to 1 meter per second. I think at one of the more recent ALD conferences, one of the companies working on these roll-to-roll processing tools reported a rate of about 1 meter per second. And it's not hard to imagine that if you want to, say, scale up to the diffusion, or to the time required for diffusion, it's not really a matter of the roll rate of this kind of track. What matters more is basically how much time you have exposed to those reactants. So just increasing the residence time by, say, increasing the kind of the volume of your reaction chamber will potentially allow you to achieve the diffusion you need. And in some of these cases, you may not need very long at all. 5 minutes could be enough to introduce the sort of functionality that you need. So I think there's a lot of work that still needs to be done in the roll-to-roll processing. And it may not be ready in the next year or two, but I think that the industry is ripe with potential for applying these roll-to-roll processing tools to these roll-to-roll processes in membrane processing, where you're making membranes with these phase inversion or other polymer processing tools.
I'm imagining a football field long roll-to-roll tool to bring the entire all the membranes through. It's feeded out of the factories, the side of the factory's walls. But yeah, you're right about the roll-to-roll in the George group. Although the guy who built one of them, I don't know if he'll hear this, but if Alex, if you're listening, unfortunately was cannibalized for parts a few years ago. I did steal a pump off of it at one point.
Easier to replace.
yeah, exactly. Yeah, we'll tell ourselves that. But yeah, I think it's a really neat application, and it's cool that we have these kind of reactors that are being moved towards these roll-to-roll processes. It's very it's very interesting, and I know there's loads of other kind of temporal or spatial rather reactors, like the ones at Forge Nano, for instance, that they use for particle ALD are just incredible. It's, I think, such an elegant solution. But this is nice. So we're talking about some reactors now on how to do this. And I would, before we run out of time, like to chat with you a little bit about your lab itself, because you, as you mentioned, are a very new professor at the University of Washington. So your lab is pretty green, so to say. And so I'm really curious what it's like starting a lab that you need ALD reactors or these vacuum type reactors. Where do you begin? What is the cornerstone? It's that you are sitting there, you have your space in front of you. It's like, this is what I need now.
It is a tremendous challenge.
Yeah.
Fortunately, there are a number of people and resources that are there to help. Many companies like Fisher or VWR provide lists of common lab equipment supplies. And so you can kind of browse through those lists to sort of see the sorts of things that you need. I think perhaps by the time we finish our PhDs, we've worked around so many of these supplies and chemicals that you can kind of just visualize and walk through a lab. Oh, I need wipes, I need gloves, I need solvents. Perhaps one of the biggest lifts was in simply building reaction chambers. And rather than buying a pre-built chamber, one of the things that we did was we built our own chambers, because that gives us kind of the modularity to do what we want. And coming up with kind of the list of parts is, again, sort of this exercise in kind of walking through the old systems that we've worked with in the past. Okay, I need this connector and this door and this pump. And occasionally, I forgot this, I forgot copper gaskets that I need for sealing these conflat flanges. So you go back and order some more. It is a kind of a learning process, but also a lot of fun, because you're designing your spaces and building equipment exactly like you want. One of the things that we did very early on was we built this high throughput ALD type system, where essentially, to increase the throughput of the chemistries we could test, we've built a single chamber or single reactor that has 6 separate deposition chambers within it. And using a computer control system, we can essentially dose a reactant. We have kind of a manifold of reactants. We can send those reactants into any one of those chambers for a desired amount of time for a certain amount of reactants. And that allows us to do things like grow 6 different chemistries simultaneously at sort of the cost of 1.5 reactors rather than 6 entirely separate chambers. And so one of our big goals is to use a tool like this to quickly screen through chemistries, particularly in spaces like molecular layer deposition, where it takes 2 years to publish a paper on a new chemistry in MLD. That's just not going to be fast enough to find, say, an ideal chemistry for EUV or for polymer membranes. What we need to do is more quickly just grow these chemistries, quickly test them for desirable properties, and then go back and optimize the process more carefully once we sort of know what chemistries are interested.
Was this the first reactor that you built in the lab?
It was the first reactor we built, yeah.
Did you have experience when you were working with Stacey or in the Grossman lab in building reactors, or was everything already there and you just kind of, just running through what was there originally?
I did have some experience, never quite from scratch, but I'd kind of replaced enough and worked enough with the various parts that I could work my way through the parts list and figure out what I needed.
I was actually, we built our own in the George group as well. And actually the reason I originally found your name, for instance, or I came across you, is I was helping Tony Straub at CU Boulder build an ALD chamber, and
yes.
I know he was also pinging you about it. So I actually remember looking at your parts list that you had sent him, and be like, oh yeah, like, okay, I forgot about that thing. Like, my God, there's so much that goes into a reactor. Was it always your plan that you would build your own, or did you think that maybe you might buy some pre-built, some commercial reactors at first?
Certainly my hope would be to eventually purchase some pre-built chambers, but a pre-built chamber can be several hundreds of thousands of dollars, whereas a home-built chamber is between 40 and 50K. And so I could build several chambers and sort of be slightly more productive at the expense of things not working, which is a common practice. We're constantly updating the LabVIEW code to fix bugs that we're finding, but it's, I think, a good experience for the students as well to kind of understand how these systems work. So the plan was never to buy our own in the beginning, but that's the long-term goal, because those commercial systems often are much more reliable.
They tend to be, but it's never a bad thing to get in there and crank some wrenches, do a little bit of troubleshooting yourself, for sure, as frustrating as it can be.
Absolutely.
So that's great then. So you did you then have a couple grad students that you recruited quickly that were helping you kind of set up the lab and build, or did you do a lot by yourself at the beginning?
Yes, absolutely. So I was lucky enough to get 2 graduate students initially in my kind of first year. A lot of the kind of initial reactor building was on me, though, because as much as I can give them the parts list, but they would have no idea what is involved in that system. So it's a lot of me with them in the lab. Here's how a conflat flange works. Here's how these valves work. This is the design that I'm envisioning. So it would have been impossible without their help, because it was just a lot of wrenching, but I was in there too, showing them kind of, the one-handed wrench strategies and designing the system with them. So.
That's very cool. So then where are you now? How many reactors have you managed to build in the 2 years or so?
Yes, so it's we've really only got that one system going at the moment, but it's been a major powerhouse because we can do the work of kind of 6 reactors with just that one chamber. So it's actually surprisingly only having one chamber has been quite helpful. But our next immediate plan is to build a system with an in-situ ellipsometer, kind of as the counterbalance to this high throughput reactor that's designed to quickly screen chemistries without as much regard to the processing conditions. We'll have this in-situ ellipsometer system so that we can be very careful about determining exactly how long and how much we need for each processing step. So that our plan is to start on probably in the next few weeks, actually. So hopefully we'll have that system up and running soon. We're excited to start testing our membranes that we're creating using these infiltration tools. And a lot of it's just been developing new chemistries, new MLD chemistries, new infiltration processes, and we're excited to get some of that out here hopefully in the next few months.
It's interesting because you are in a kind of strange spots from when you started your professorship, your tenure at the University of Washington, that this pandemic that we had, and I'm sure you've had this conversation so many times, and either it was really good or you've probably commiserated about it many times before of, now you're starting a lab and months later, this pandemic happened. So how was that transition like? How did it end up affecting getting your lab going with recruiting students and so on? Or maybe it didn't have that big effect at all, but.
Yeah, so I actually, I interviewed at the University of Washington, and then several days later, the pandemic hit. They closed down campus. So I really just kind of slid under the door as it was closing, like in an action movie. As a result, I really started in the middle of the pandemic. The negotiation was already a challenge because many universities were pulling back funding for new positions. And starting, the biggest challenges with starting have been related to access to the building. So we started, mostly remotely. We had big challenges with supply chain. So we would order things like a glove box and it would arrive 6 months later. Gloves took, I think, 6 months to arrive. A lot of the parts, so some of the parts for the reactor came rather quickly. Others were much slower to arrive. And that definitely set us back probably a good 6 months just because we were waiting for stuff to come in. But honestly, I think the biggest challenge has been for the students. Sure. It was hard for kind of these students to be working remotely in the beginning, not being able to come in. It was hard on them because they couldn't socialize and kind of meet some of the other graduate students. It's demoralizing to be kind of trying to do this learning process from afar. And the same is true of the undergrads. So I'm fortunate enough to have kind of a small team of undergrads who have been working with me for since I began, really. I think my formally first student was an undergrad who reached out to me. They've all been wonderful, but it's just very hard to continue your education when you're constantly changing how you're interacting with the school, when you're kind of not able to come in regularly, and just kind of when you're in this environment where you're not able to interact with kind of your friends in the way you would normally. So I think, like many people, we're all excited for things to hopefully be calming down again soon. And I think they've done a fantastic job of making truly excellent progress in spite of everything that's been going on over the past few years.
That's really wonderful. I mean, I have a lot of time to think about the problems, I suppose.
Yes, a lot more papers in the beginning. We did a lot of reading.
Yeah, that's right. Lit review for every group meeting.
Yes.
Well, that's great. I'm really looking forward to seeing what comes out of your lab, David. Yeah, like you said, hopefully in a couple of months, so we will all be looking out for it. Yeah, it looks like we're kind of coming up on our time here, and I don't want to keep you for too much longer. So is there anything that you would like to specifically call out? Any social media or websites we can find you on to follow your work at?
Yes, so I'm at my group webpage is bergsmangroup.com. You can also find me through the University of Washington Chemical Engineering Faculty Directory. I maintain a Twitter profile. I think I'm at David Bergsman on Twitter. And I'm also on LinkedIn. Those you can all find all those links also on my group webpage. And you can reach me via email at dbergs, that's DBERGS @uw.edu.
Perfect. I will put all of those things down in the YouTube description, and then whatever the audio ones are, I don't know, they're somewhere, but probably not where I'm pointing. I don't. Well, actually, if they're listening to audio, they're not going to be able to see me pointing down there anyway. So apologies, audio podcast listeners, that you can't be in the interactive stuff. But anyway, that's great. Thank you so much, David. I really appreciate you taking the time and coming on and chatting with me for a little bit and spending a little bit of your Thursday morning there. I know it's almost the evening here, so
Yes.
really great to have you. Thanks for coming on and joining me.
Yeah, thank you so much for inviting me. It's been wonderful chatting with you about kind of some of the uses of these tools.
Good. It was nice to talk to you too. Really nice to meet you, Dave, and hopefully we'll be able to connect in person at some point.
You're listening to ALD Stories with Benek, the home of ALD. To stay tuned for new episodes, make sure to follow us on Spotify, Google Podcasts, or Apple Podcasts. We hope you enjoyed today's show. Talk to you in the next one.